Let's get started. All right, let's get started. Welcome to San Francisco Big Analytics. My name is Chester Chen. I'm the organizer for this meetup. So before we start, we first want to thank Yelp for hosting us. If you're looking for jobs at Yelp, you can talk to Rebecca at the back. I don't work for Yelp, but they don't have anybody to say a few words and ask me to say, if you're looking for jobs at Yelp, and you can talk to her at the back. We really appreciate Yelp have consistently supporting us, with the food and drink and pizza and the audio video engineers and the securities, and really appreciate it. So we have at San Francisco Big Analytics, we have a lot of meetup planned, and so it's besides this one, the next one also at Yelp, we have TensorFlow on Spark. It's open source project by Yahoo, and that'd be a good one. And we also have another one in San Francisco, is how to using deep learning for real-time anomaly detections, and that's in San Francisco as well. And in May, we also planning, which have not announced yet, is going to be events at GoPro. I work for GoPro. I'm the head of engineering and the data engineering and data science at a GoPro. So actually, my team going to talk about our work at a GoPro, as well as the analytics we did at a GoPro. So, and at the same time, so we also have some free GoPro cameras. So if you want to join that one, so that'll be in early May. The location will be GoPro Experience Room in San Mateo. And there's other meetups which haven't really finalized, but as just look at the meetup page, and you should have a lot of goodies there. So tonight we're talking about Vicarious AI, how to train machine learning models with little data. So I'll tell you a story about this, how this meetup come about. So right now there's a lot of articles and papers on the AI, and both in US and in China. So I actually discovered this paper in Chinese paper, and very shortly after he talked at the NIPS conferences, and the paper itself had been translated into Chinese. That's at first I read the original paper in Chinese, and then I tried to find the original paper in English. And then after I find it in English, I say, let's search this author, see where he locates. And then it turned out he's in San Francisco. So, so I invite him. So, we're lucky actually. He lives right here in San Francisco, and he agreed to give a talk on the topic. So, Dr. Lou is the leading data scientist at Vicarious, and we are very curious about and how he achieved 6,000 times less data to train a model. So, with that, welcome, Dr. Lou.
Thank you. Can you hear me? Oh, so thank you, Chester. So I'm from a company called Vicarious. We're a very small startup actually in the beautiful Union City, not San Francisco. So just a show of hands, how many of you have ever heard about Vicarious? Okay, so I'm in the right. This is about what I should do. I'm going to talk about first, I'm going to talk a bit about what our company is, and what's our unique approach towards AI. And this is just one particular paper we did. We do a lot of more papers. This is just one particular paper we did about the text recognition using our models. Our model is our own model built all by ourselves. So we are not deep learning. We are not deep learning. We are probably one of the few who was not doing deep learning. We actually study deep learning. There's a lot of good techniques, good methods inside. But our approach will be quite different. You will see a lot of neuroscience, cognitive science. You will see a lot of modeling about the graphical models, those kind of stuff. Just a bit of background check. How many of you actually know what a graphical model is? Cool, thank you. How many of you know structured output prediction? Okay, so I actually try to make it as simple as possible. I'll also go into a bit of details. There'll be some detail about the exact model we built and how we learn, how we test it, and what's the result, what's the difference between ours and the extremely popular deep learning. So first, so about Vicarious. Vicarious is a company based in Silicon Valley. We're actually in the beautiful Union City, East Bay. People pay attention to us about like 2-3 years ago. We actually announced that we can break recapture. This is just the beautiful text you saw over there. So we can have one model that will recognize all kinds of capture, trained using very limited amount of image. And so basically we can crack whatever Yahoo email registration or whatever email registration. And we have raised up quite some money. We'll come to that later. So what's missing in building AGI? It's artificial general intelligence. It's AGI, it's not just AI, not just narrow AI. What's missing? So I will give you one example. Like 200 years before, actually more of 100 years before, we want to fly. A human want to fly. It looks like extremely difficult task at that time. And our objective to fly, we want to build airplanes. We learn from birds. We look at the bird, we observe them and see how they fly. And at that time, we already have a lot of technologies, like we have mechanics, we have fuel, we have combustion engines, because the car was already built at that time. What's missing is essentially our understanding of the physics. It's the aerodynamics. Once we develop this theory, put it all together, we quickly build an airplane as obvious a bigger game changer. Now, today, we want to build AGI. Our goal is to have smarter robots, smarter cars, smart everything. We want to make them to be human-like, as smart as human. And we have a lot of technology already. We have good computers. We have a lot of modeling techniques. We have a lot of good robots. We have so many algorithms. So what's missing? What's missing is essentially our understanding of brain science, and more importantly, how we use brain science in our research, in our engineering. So this is exactly what Vicarious is doing right now. Vicarious try to put together brain sciences and the modern modeling technique. This is the way we think we can achieve human-level intelligence. We must learn from physics. Brain science is the physics, and we want to use a computer to model the physics, and we need the modeling. So to be a bit more specific, to build AGI, what we think we should do is that we need to take neuroscience and cognitive science very seriously. This is our guideline. This is the book of a working system. That's just exactly us. And we need to focus on data efficiency and task generality. Data efficiency means we should be able to train with very little data, be able to solve a variety of problems. This is how humans do. I will show you later one example. And we need to focus on task generality. The model we build should be able to solve quite a variety of problems, given the same amount of data. And we need to use the state-of-the-art computing and modeling techniques. There are many of them. So, following those principles, we're doing a lot of work. One of the work is that we're building one framework or one algorithm called recursive cortical network, RCN. It has a lot of unique features. Some like a lateral connection, which I will talk about right now, which motivates us to build something, so we call a generative shape model. This is exactly how we can beat deep learning using this model. We have contour surface factorization. We have a border ownership coding and top-down object-based attention and timing of inference. Those are specific terms you can actually draw and learn from most of them from like neuroscience. And they are actually very critical features if you want to actually build a working true AI system. So about the team, we have very great advisors. We have Fei from Stanford and Bruno from Berkeley and Yue from UCLA. And our team, we have about 40 people right now. 70% of them are PhDs, and most of them have their strong skills in machine learning or computer vision or neural cognitive sciences or robotics or software engineering. The way we operate at Vicarious is a bit like what you see in DeepMind or OpenAI. We actually do research, and we publish papers. We started publishing a lot more recently from last year, from end of last year. We have published a NIPS, CVPR, all those kind of things. And we raised about over $80 million so far from those renowned investors. So one thing I want to talk about today is this paper called Generative Shape Model for Text Recognition. And this is just a study of our model on this particular task. And to make a short story, we can outperform neural network on text recognition on this particular task. And more importantly, we use only 1 out of 6,000 amount of data of that will be used by neural network. To put it in perspective, if you consider this a huge circle as the data required by neural network, this little dot is data required by us. And to make it even more clear, think of this. This is the data difference of data, amount of data we need. So speaking of neural network, just a quick story of neural network. You probably many know all those kind of different models used in neural network, deep learning, convolutional neural network, IBM, distributed machines, and autoencoder or stacked autoencoder if you can go deep. RNNs, STMs, which is kind of have many gates, a smarter way of doing RNN. And there are a few more. So what's common about all those models? Most of them is the first thing is the data. It's always about data. So you need a lot of data to feed those models because the models themselves are actually relatively simple. There's no strong structure in it. That's why you need a lot of data to feed them. So it is just like this megalodon, comparatively, and you need to eat a lot of things to work, to function properly. And there's some robust issues associated with deep learning. So here's one example. This is a famous game playing by DQN, DeepQ Network, extremely great work. And so I trained this whole thing using DQ and play this. I thought this is a breakout. It works great. The scores going up. It never fails. And could you see the difference between these two images? Any difference? Can you see it? The image on the right is just completely fails. So what's the difference? Can you see it? It's a human. It's not so obvious, right? I can tell you the only difference is that the intensity increased by 4% only. As it increases by 4%, the whole system just breaks. It cannot play the game at all. So this is something that is not so obvious when we just read the paper and see those highlights. There's no human here. It's just to say that how, as a human, if you would be able to play this game, I'm sure you'll play that game very well. It's almost the same. We cannot see it. But to the algorithms, they look extremely different already. That's my point. And you can also fool deep neural network using some playing. If you play around a bit about the procedure, this is a good work by Yusinski from Cornell about fooling neural network by playing with the procedure and backtrace. You get some kind of weird pictures that can be fooled, have kind of fooling thing. So how does it work in practice? This in deep learning. Deep learning is the nature of deep learning, especially is an accumulation of local features. You just count, it's a computer local feature, whatever kind of filters, and you count them in some way. And you add them up, and you do some filter and count them again. And you have this pooling of just have some invariance spatially. So let's say we will recognize cars, different kinds of cars. This is a very extremely simple image. You can recognize car, vehicle, wheel, perfect. And what about this? As a human, you have no problem seeing. I will show you one example as a proof. As a human, you have no problem recognizing this as what it is. It's obviously a car. But if you look at the system, and it's actually another commercial system, it's a bedroom, pillow, bed. It is a completely missing elephant in the room. It's a car. It's the most important part. But why we can see this? Because we notice, we have a conceptualization of the whole car as first of all, as a shape, that's why it's a shape model. I'll come back to it later. That's why it's a shape model. We can see this. And this is another example. It's a basic sketch. It tells you it's illustration vector. It's not wrong, right? It's some feature of the image. It's correct, but it's not telling you that this is what it is. But if we're human, would I let you show this image? You will see that it's a car first. It's another example. It's covered by grass. if you train on this model, you may be able to recognize it. But the question here is that why we don't need to train. I will show exactly one example why we don't need this. This is another example, and this is another example. So come back to you, why we don't need this. So let's do a real test, a human test. This is my son, Kevin. He's 18, that was 18 months, 2 months ago, he was 18 months. And as a boy, he just loves cars. So he has been trained on recognizing cars. Toy cars, his toys, and sometimes we take a walk, I show this is a car. And I probably have pointed him like 50 times, or maybe his mother pointed another 50 times, or maybe 100 times. We showed him this is a car. Not that many times, we definitely didn't show a million images saying this is a car. Just maybe 100 times, maybe at the most 200 times, but just at this scale, right? So now let's see the field test. By the way, in Chinese, in Mandarin, the 车 means car. You can Google it if you don't believe it.
Kevin, 这个是什么？车。这个是什么？车。这个是什么？车。对。这个又是什么呢？车。这个最简单是什么？车。对。
So because I try to avoid this kind of memory or sequential effect, so I just put an easy image at the end of it. I put the hard image at the beginning. Well, harder for computers. It's just so easy for he was 18 months, and it's just so easy for human to do the job. Those are interesting questions we try to answer in Vicarious. We try to build a model that be able to do this kind of task. Train on very small images, 100 cars, you'll be able to generalize over 1,000, a million cars. You'll all be able to see them. And there's this obvious story of a diminishing return of data augmentation. We all do data. If you do deep learning, you always will do some step of this data augmentation, and you will know that as a discriminant model, your test error will just basically go flat. So sometimes if you add more data, you cannot just go up anymore. Unless you change the model, increase the capacity, and then you ask yourself a question: what's the end of this? So, but discriminant model, they do have some good features, like it's straightforward, easy to and fast to implement. They're definitely data hungry, so they're actually pretty good for big data. If you have a lot of data, then it's good idea to use some of this. They're actually good for narrow problems, but not for general tasks. So another perspective, we all say that AI is electricity. Like many people saying this term. It's extremely good metaphor, and so let's go to this story. So this is this famous game of Liesendorf versus AlphaGo, and the normal human brain, the power is about between 20 to 40, let's say 25 watts. That's counted as 1. So can anyone guess what is the power consumption of AlphaGo when playing that game? Any random guess? How many? A lot more. It's 1 million. People actually did this computation. I also did myself. So it's about 40K the times you need of the human power consumption to be able to play just this AlphaGo game. And not to mention, he can do a lot more, including whatever, eating food, wash clothes, whatever thing. Please. Yeah, of course, we needed to, inefficient. Let me remember. I think they used 290 something GPUs and 1,400 CPUs altogether. So this is another perspective. So in this case, people say AI, is electricity. I would say yes, exactly. AI is electricity, and that's why this is not going to happen. Don't worry about this. You guys know what it is, right? Okay, so that's basically the story about Vicarious and why we need to do some kind of a brain-inspired and artificial intelligence, how we can approach a true AGI in this way. This is just one paper we recently did, presented at NIPS, which is one of the main conference for machine learning in the last year, 2016 in Barcelona. Those are my co-authors, Ken, Wolf, CC, Bhaskar, Scott, and Dilip. Scott Dilip is the founder of the company, So why you want to do text recognition? There are many applications, obviously. You can do augmented reality. If you are family robots, you want to fetch me a book, it has to be able to know what a book it is. Self-driving car, read street signs. A map is doesn't always help. So why it is difficult? This is a very good paper done by Google. Google folks is a very good paper, and it's already in the title. It's Uncontrolled Conditions. Unlike traditional OCR, which is a very classic problem, everything is basically controlled. You basically scan the whole thing at a scanner, and everything is flat, and you have a beautiful scans, a beautiful text result as using here. But in the scene text or in the real-world text recognition, it's actually very ugly. The view was really ugly. You have all kinds of change of illumination, noise, different texture, different fonts, whatever. So this is a difficult problem. There's actually I think one quote someone said is that if you can solve OCR, you can solve AI. That's maybe a bit extreme, but so these are two data sets we worked on. These are kind of two standard data sets on the field. One is called ICTA, and there was SVT, Street View Text. So the challenges is there's many fonts, and you have to cover all kinds of variations of fonts. They have different appearance, color, texture, brightness. There are noise, background structure. If it disturb you, as the image may be blurred. There are change of perspectives. The image can be rotated. They have different layout, like different spacing between letters. All kinds of problems. So now go to a bit of the technical details. This is the outline. We have two major components. The first component is called a generative shape model. This is basically the core part. It recognizes the text, each letters. The structural parsing model is basically where you put the recognized letter together to form a word, because you want to recognize a word at the end. I will also give a bit of detail on this, as there's some other tricks and some results. So while we want to model shape, I think from the example I showed before, it's probably very obvious to you now. Think of the way we will create a text in the machine. We first will pick a font, let's say letter A, then we add a color, or maybe add a texture, whatever things. So whatever the color will change, the font will be consistent. So that's why the shape will be consistent. That's why shape is almost, you can say, the most distinct feature, if you want, in vision. And the modeling shape allows us to do so-called factorization, meaning you want to be able to separate the shape and the texture information. And so if we have the factorization, if you give this kind of separation, it gives a lot of advantage. So now we have an interesting question. So what if we do not factorize? Give you one example. If you use some discriminant learning, let's say convolutional neural network with an end-to-end training, sounds really fancy. So if we have a lot of A's in blue, you have a lot of B's in red. If you train on this, then you have a test image of A in red. There's a high chance that A may be classified as blue because it will be easier for the classifier to pick color, not actually the shape, if you do not separate those information. So factorization is always an important way when you want to do computer vision. So why generative? So generative means you actually model data itself, not just a projection of data to features. So let's say we want to model triangle. We want to classify triangle, not non-triangle. So if we want to build a generative model, you actually model the whole thing as a triangle. You want to model triangle itself. Let's say, I need to define 3 vertices. I need to have the vertices connected by 3 lines, and the sum of interior angles of amounts to this degree. All this has to be satisfied. It's data itself. I have to know of it. If you want to do it in a discriminative way, you're actually modeling features. It is simple. Well, you can just say, to say triangle, not triangle, I just count the number of corners. This is one way to classify. It could be effective, but it could be also wrong in many cases. So discriminative learning is actually a lower dimension projection, or let's say approximation of the true data, because you actually don't model data itself, you just try to find features. It's not original data, that's why you're losing a lot of information. But it's simple, it's fast. So it's not saying you are using it is a bad idea. So a bit of the technical details, because I asked how many of you know graphical model. Graphical model is a way you just model the correlation of the random variables. For example, it has 2 types. One thing is called Bayesian networks, that's called the Markov networks. The Bayesian network is directed, that's why it's directed, that's why you see those errors. The Markov network is not undirected, that's why you don't see errors. So this Bayesian networks, it's mainly about causality. And this is mainly about coexistence, co-occurrence. And the factor graph is just another specific way of doing graphical models. And you can find a lot of detail in this book. This book is one of a Bible of graphical model by Daphne Kuhler from Stanford. Okay, so what's our model look like? It's actually extremely simple, not complicated at all. There's no fancy learning rate, there's no tuning, whatever. It's just the same as simple as it is. So here's a modern constraint process. We first take a clean image. We take a clean image. We always train on clean images. We never train on image with background, because we only want to understand image itself. We actually don't care about. We do not want to care about the background. So we take a clean image of A. We extract like 16 oriented features, like different angles. That's just exactly our feature, nothing more. And then we will add a first step, the second step, we'll do specification, meaning that I don't want to pick 2 features of the same neighborhood because they're probably the same. So I've just pick only a few at a certain distance. Like those black dots. This whole process is automated. We don't have to hard code it. And we'll add a pooling window. So basically we say that this model, this point can move along this window. That means we allow this whole shape to deform. They can deform. But they may if that's the end, they may deform to something we have never known. It's kind of some weird shape we cannot even recognize. That's why we need something called lateral constraints. This is our lateral constraint. Basically, we add lines between neighboring features, the kind of dots, also add some sort of distant features. Basically, those lines will penalize this whole model if you are putting too far away. So it means that we allow them to deform, but not too much. You can see that basically as a shape model that's extremely flexible, but also give you the true identity of being A, instead of becoming something weird. So this is basically the process, and we can convert this whole thing as a one-factor graph. A factor graph is just one standard way in graphical model of modeling something like this. And you have the node as a variable. You have like a binary factor and pairwise factors. And so now comes to the part of why we want to add this kind of connection. Because this is actually discovered in the neuroscience. This is all our motivation, where it comes from. So when you are doing, when you are seeing something, your brain actually activating very long distance connections. It's not like when you have this node activity, this neighborhood activity, you actually have co-activation of this guy and further away those kind of connections. This is the way you to enforce a long range connection to compatible cells. That's why we can introduce this idea into our model like this, as a proof effective. So during test, how it works. Let's look at this image. So if we have a letter A, we have a model A. Basically, the test meaning we want to fit the model into this letter A. And we have a two steps. First step is so-called forward pass. So it's basically similar to what you see in CNN in the forward pass. You get a lot of features and you count them. First you match them and you count them and go up. You basically get one number out. And this finally is just like a heat map. So almost like CNN, like the last level CNN, similar to that. And after that, you actually, different from CNN, we're actually going another step going back. So after saying this is where my model should stay, I will go back and try to find the evidence, meaning that I can find those exactly per pixel accuracy, which pixel they belong to the letter A or background. So I can have exactly the very accurate segmentation of each object, or in this case, the letter. So the connection to saying is exactly like this. Saying is only one step going up as end. I give you recognizing A or dog or cat as end. But for us, we have going up and going down. We'll be able to explain the whole scene rather than just going up and give you a label. And we solve this whole thing. There's a lot of like mathematics, this whole thing using so-called belief propagation, and it's just one standard approach for doing inference in graphical models. I'll skip the details. So this, again, has a strong motivation from neuroscience. In neuroscience, we actually study, people actually put a probe in the brain and measure this thing, get this result. And we actually have a time course of figure ground segmentation. We actually can, has a process of understanding the scene, and we'll recognize this letter A or cat or dog, and then our brain will trace back and see which of the part belongs to this object, which part is background. So we have this process. This is almost similar to what I showed you of going up and down in our model. So a third interesting point of a model is that since we are a generative model, that means we can do sampling. We can sample from it. A sample is basically you try to say that, tell the model to say that, ask a question of, if the model is trained about letter A, I ask you how letter A should look like to you. And it can spit out a lot of different variations of the model. The model thinks it's letter A, as you can see. Those are also model output, sampling output. So what's the important implication here is that if you want to have to, it means that when we have built a model, a generative model, we will be able to recognize all kinds of variations like this. As long as it can be sampled by the model, it can be recognized by the model. So any kind of different, because in practice, you have all kinds of noise and, occlusion, illumination change. You don't have these beautiful lines, straight lines. They're all very ugly. That's why you always actually see something like this in practice. And they're all covered by our model, just a single model. We'll be able to cover all of this. If you do not use this approach, you use some kind of, convolution network, you may have to probably train all kinds of different variations, put it in the training data, and train it and be able to predict this. So this is a strong implication of being generative as an advantage. And again, this has a neuroscience motivation, and you can all see there's a square here. You can actually see it. So we human actually, when we see it, we have a model fitting in our brain. We have a model. Like in this case, it's a square. It's one of the basic shape. We're actually fitting this to this kind of thing, even though you don't have much evidence. There's no lines here. Okay, so now the part before is actually the core part. This generative shape model part. It's actually extremely simple, but proven very effective. But by itself, it's not sufficient for the task because we want to recognize the words out of this whole image. So we need a parsing step. That's because the generative model, the output, it's a calculator level model, so it actually doesn't know what word it is. And you may have many false positive forms. For example, if you recognize a letter E, it may also find F looks like one F, right? It's part of the E, L, I, stuff like that. So the task of parsing is be able to find the right sequence of letter characters that form a real word and also look like letter printing. So there's a parsing graph like this. suppose we have an image like this word high, and we recognize one edge here, we recognize one end, which of course is wrong, and I may be considered as I and L, for example. And then we will just build a graph like this. We will just say, basically just try to walk from left to right. I have a possible of going to H and going to this I, or going to L, or going to H, G, and H again. So H, L, G, N is not like a likely word, but H, I, G is a valid word, so I will eventually try to find this as the right path. So to solve this model, essentially the task is to find this is the right path I should take. And you can put it in a mathematical way and look at the scalar equations. You just basically optimize this whole function, and it can be optimized using second-order dynamic programming. That's actually pretty straightforward. So what about features? So I mentioned that we needed to, for example, we needed to be able to form a real word and look like a valid printing, right? So you have to be able to characterize them using some features. Those are the features we use. For example, a normal printing, you will see them as a straight line mostly, right? And the letter font should be consistent. And you also have to see it's BEE is like a good character n-gram. And it's not like to see for the BLL is like a rare word, it's a rare gram. You can put also information into your parsing as parsing features. And now the question is that we actually use about 20 parsing features. Our question is how to learn those features. And as a side note, and many friends of mine, they will say that feature learning is outdated. I would argue that feature learning is never outdated. It's a matter of the quality of the features you design. You can design, if you design very good features and they are invariant to a lot of changes, it's always be a good feature. So feature learning is still useful. If they can learn, it's also still good, but in many cases, if you have good features, you can engineer and design them, it is also very useful. So back to this, how do we learn those ways? That's why we need a bit of structured learning. So here's a bit quick story of structured learning. How many of you guys know a supported vector machine, SVM? Hopefully you all know how it works, right? SVM is extremely simple. When you are training the SVM, you have positive way, or either positive or negative ones, and you have one hyperplane. It's linear in this case. And you try to basically maximize the margin between so-called supported vectors and the hyperplane. So you have those kind of margin, you want to maximize it. So SVM is always to predict a single output. It's a scalar value. Structured learning, you can see it as an extension to a supported vector machine. So now, instead of predicting a single scalar output, like yes or no, good or bad, and now it will predict a structure. This is useful for many applications like grammar parsing. So you are inputting the whole sentence of time-driven parsing store in a car, and you will be able to create this is a tree. It's a parsing tree. That's your output. You actually have the one algorithm be able to predict the whole thing. And this is in computational biology. You want to predict sequence labeling, NDCGs, and for computer vision in scene labeling, you want to be able to predict this is a boat and the tree. The boat should be inside a river, and the river should be next to a bank, stuff like that. You can include all the information. Also like in object tracking. So how to do structural learning? For SVM, you will know how it works. You are given positive and negative. You are given positive and negative training examples, and you want to maximize the margin in between, as you see the example here. And very simple. For structured learning, there's an interesting part. You are given the examples, and you are given only the positive examples. There's no negative example. Why? Because you are actually given the whole structure, and you are given the input data and the true output structure. But any variation from this true structure is going to be positive. It's going to be a false sample. That means in structured learning, what happens is that you have a true example, and you have exponentially many false examples. That's the story. For example, this, if I want to pass this beer, I have many paths going from left to right? And I know that one path, the BER, is my correct path to take. So I put this as a positive example, this red box. But there are many false examples, like if I'm mistaken B for P, so I have a PER, is a PR, so it's actually not the one I want. So it's going to be a negative example. But if I have a B, I can have BFEP or BEEP, so those are all negative examples. So now, instead of maximizing the margin between, like in SVD, between the positive and negative examples, in this case, the trick is to maximize the margin between the positive, meaning this one, and the best wrong examples. So you have, the wrongs have different qualities. Some of them is really wrong. Some of them are okay. And for example, the PER looks really similar to BER. So I want to say, if I can handle you, I can handle all the rest easily. If I can handle this one, I can handle all the rest easily. So I'm going to maximize the margin between this one. And that's the way you train a structured learning model. And in that case, train all the features. And there's 2 books, and I myself contributed to this book, and it's all details. It's a very useful technique if you want to predict complex outputs. There are a few other tricks we use. For example, we try to incorporate the concept of objectness, so we can have like a very clean edges instead of the noisy ones. We use some adaptive edge filters. There's no hard-coded, or there's no training, or it's just hard-coded. Just put some parameters, and we can design something like this. There's a font selection. We want to find a good font from we want to find a very typical font from a huge collection of fonts. And language models, because we still have needed like know what's a good n-gram, right? So we use n-gram using like a dump from Wikipedia. We also pick a dictionary from this. Since the language model is a big supporter to the final result. So let's look at the result. This is the letter in the test images. This is where we recognize different letters of A, E, and R. So you can see there's a huge variations in terms of this, font or size. You have small, shorter A's. You have like tall A's. You have thin A's. You have wider A's, like this. And they have different colors, brighter and darker, or whatever, different background textures. We can all handle all of them. Like this one is really blurred. We can all handle all of them. Just the same model, we can handle all of them. Same for E and R. And quantitatively, our recall, meaning how many we can find the true ones, is 95%. And previous report result on those per character recall is 61%. So we can almost find 95% of all the letters in this data set. Now comes to the key result. We compared, this is on the ICTA 13 and the SVT test result. We compared to like a PRC read by Microsoft Research. This is deep structured learning is by Oxford, and the photo is by Google. And on these 2 data sets, we get a better result, 86 versus 84, 80.7 versus 78. It's actually not a big deal, right? So 2-3% better is not a big deal. There's a bias in data set, whatever things. This is actually not our main point. As long as we're compatible, we are okay, because we know why we fail. But most important is here. We use the 1.4. We use the 1,400 training images. Total OCR and this deep learning approach, they both use about 8 million training images. That's the significant difference we see here. This is the advantage of using a generative model, using our approach that we encode a lot of inspirations, a lot of techniques we learn from neuroscience, put it in there, and we can get this kind of a huge difference. And in fact, so in this test, our training data is actually less than the test data size. The whole, if you consider put them all together. So that means that this is more like the human-like, right? We can train on relatively small ones, be able to solve more larger problems that is definitely larger than our training size, training information. Go ahead. Human will be 98, 99. 99 almost, if not perfectly. We will definitely need to train on Chinese. It's not going to be that kind of a transfer. It's like a baby born, speaking English, kind of just suddenly speak Chinese. You have to train on that. So this is a very key result. And to us, the most important message is actually these lines. You know, we have a evaluation of our technique, and we are using training data less than the test data. This is the human-like way. And our result can be interpreted. And for example, the left side of this picture is the errors made by our approach. On the right-hand side is errors made by the PhotoOSR, Google's approach. And we can see that the case we fail, it is basically just a bad image. It's just really hard, like it's blurred, or it's like some part of missing, sometimes it's handwriting. We actually don't model handwriting. We have a motion blur, it's HEPP, the kind of motion blurred. It's just a hard image. And you can see for the other, on the other hand, on the right-hand side, they actually fail at some like a relatively simple case. It doesn't make sense. Like for example, it's a line, short or long, and keys. So that's just very simple, clean images, very clear, very easy for human to recognize as they fail. They fail. This is a case of like a discriminative learning. If you don't have a good control of the underlying mechanism, you may fail at some unexpected case. This is some also related to what I mentioned before about the robustness of deep learning. Yeah. Good. Yes, one? Yeah. Yeah. I think it's the sword is mainly we're actually missing the S. We're missing the S. In this current parsing, we actually don't add that. Yeah. So you can also say that there's a lot we can do, but now we didn't add this kind of correction. If we correct, we may be able to solve this. Definitely. Not following your question. Yes, I can. Actually, I can exactly say that because it's about the interpretability of our model. Yeah, I can. So first of all, we as a graphical model, we can output uncertainty, and we output with uncertainty, so we can know if it's good or bad. Another thing is that we will fail if it's blurred, meaning we cannot get the good features out. And we are extracting local letters. We are not looking at the whole thing. And so there's certain cases I'm going to show that our model will fail. The algorithm would just spit out a very low confidence. Algorithm will spit out letters with very low confidence. Not because I'm a human, not because I know the algorithm. Yeah, it's designed this way. So please. They actually overtraining. I can tell you that overtraining the model takes on. We did all the training on a training, not test. The training on a MacBook, it takes about 5 minutes or 2 minutes. 2 minutes is all done. Because I showed you this whole graph structure, right? This constructor graph. That's our training. We don't have no gradient. We don't have like a learning rate. It's just as long as we create this graph, we're done. That's our training. At the test, yes, we are slow. We are, like for Google's approach, I think they can do this kind of image at, let me think, about half a second or like 2 seconds roughly for them. But we are like 5 to 15 seconds. But our code is in Python, but it's not optimized. Also, if you use GPU, it's definitely a lot faster. There's another layer of acceleration. Yes, we are. This statement is correct. Deformation, any model, any per category vision model by itself will not be able to handle occlusion. Definitely, occlusion is another question we are studying. Yeah. Okay. I mentioned this before. So our model we can do joint recognition and the segmentation. This is also human-like. As a human, if I ask you to look at this object, you can actually immediately see what it is. You can almost just right away point out what's the boundary of this object. This is segmentation. A human can do it right away. And our model is again the same model, be able to finish this task altogether in one run, in a forward backward pass run. So we can actually give you what this word is, and we can give you exactly which pixel belongs to what. Yes. In the current implementation, no, because this is a different layer of problem. It's about more on the language side. You can compute the expectation of music from given MU. It's another layer of problem. It's not what we do here. We use language as an extra input for parsing, but it's not our takeaways. That's pretty much our story before. This is how we do this kind of task with just a very limited amount of data. So takeaways, generative model can be made competitive. It's just like a common sense before people say that the generative model is useless. I want to do discriminant model. I was using SVM, CNN. I did this before. I was previously doing, in my PhD, I did a lot of structural learning, which exactly is a discriminant model. It is true that discriminant model is very useful. But generative model has actually better potential. It will be able to solve complex problems if you can model it correctly. It can solve very complex problems with a very limited input. Modeling shape is critical for recognition. As you see the example before. Simple aggregation of a local feature is not sufficient. It can give you some wrong results. Lateral constraint proven effective. This is basically what we learned from neuroscience. And in the future, what we think is a working system like a human, eventually it will be probably a hybrid. You actually need a discriminative part. But the core part will be generative part. A discriminative part, you can see it as almost like an instant reaction. It's a memory, just a memory map. You see something, you fast pick up some important feature, you give it a solution. This is discriminative part. You can say, I can make one example. For example, let's say a quarterback playing football. When he deciding at a very instant, he decided to throw or not. In many cases, it's just discriminative. He's just looking at it very quickly, the layout, just throw or not. And those are discriminative part. But in many tasks, especially the common easy tasks, daily tasks, it's generative. We actually have an understanding of the whole environment. We understanding of the physics of the model, of the surroundings, where we can just function properly. And deep, not always. In this case, we just use one layer. It's a single layer model, it's not deep. We actually have a deeper model later coming, or what we call a hierarchy. It's coming now. So coming next area, Vicarious, is that we have extended our model a lot. We will probably publish another bigger paper on all the technical details. We will basically open the whole thing and try to have more people be interested in our approach, more people following this kind of way of doing AI. And we'll have another bigger paper on this. But we have added like surface appearance handling, feature learning, hierarchy is what I mentioned about getting deep. It's still necessary. We have to do it properly, but it's still necessary. Extension to 3D, and we are now mainly focusing on application of this in robotics. So I'm actually responsible for the commercialization of our technology in different areas, and one of them, the major focus is executive robotics. So you see the story of we have brain science and modeling. Now we'll just put all these things into a real robotic body. That's our next step for Vicarious. A quick plug-in, we're hiring, we are finding many people. If you are passionate about AI, you like modeling, you like, or you like playing with robots, you can write code on your good infrastructure, please welcome to check our homepage, and we hire many people in those domains. And we also do deep learning. If not that our core will be based on it, but we also study deep learning because this is a very good technique. We can pick out a lot of useful things from it. And you can also do something at our company. Okay, thank you very much.
Questions?
Hi, so you show pictures of Judea Pearl's book a few times. I'm trying to understand where does, so I see Bayesian Networks as an example of a graphical model, but generally, are you doing much in the way of causal inference or in terms of causal structure learning? Because you have that.
Yes, causal structure learning is actually we use some causal structure learning here for feature learning. There's some causal structure learning there. But we use our core technique is now based on graphical models. But graphical is just one technique. It's just one way to, let's say, how we reason about what we should do, how we reason about what is this kind of a digital computational model should look like. It's more of like a tool for us. We don't specifically study the model, this graphical model itself. We just use it. And
the second question is, so your company, so you're doing some research, and I hear you're looking at commercializing some of the technology.
Right.
What's your general IP strategy? Are you building these types of algorithms in-house, and you're not open sourcing them, and you're making some stuff available with your research publications and keeping other stuff for personal IP and then patenting it, or what's your approach there if you haven't actually commercialized anything yet?
Yeah, I think for now one thing we would probably just be a typical licensing. We just will license basically we don't build robots, but we actually build a brain for robots. We can do it in many different. We can just work with the robotic solution provider and give them what we have, or we can basically just buy a robot ourselves, provide a full solution. There are many different ways. We can just do it in a hybrid way, whatever is best. We are flexible.
Thanks for the talk. It's really interesting. So I have a question on your the vision of the AGI. So in the talk you mentioned this approach. I think you put in a lot of feature engineering, human insight into a model to get a very powerful method that can train on very few data. But how are you going to push this method so you can achieve AGI? For example, you can recognize cars and trees and characters and all kinds of things with few thousands of training data, kind of approach.
See, I think my take on this is that first of all, it's going to be a long journey for the true AGI. It's going to be a very long journey, and in this work, we actually just have a very simple input-output, one layer input-output, right? Given image, find the letter A, B, C, D, E, or maybe car, whatever things. But in actually the real, what's happening in our brain is a lot more complicated. We need multiple layers of stuff. For example, we need a conceptualization. So core idea behind our strong generalization is that we can conceptualize things. Like my son Kevin, he saw this little car. He can build a concept in his mind about his car. The concept will consist of its shape and some details. They should be all put together. And there's another aspect like sequential reasoning. So we are actually not seeing as just right away you look at it and you know everything. There's also a sequence of attentions, of there's a sequence you explaining. There's also idea of explaining away. If you have seen something, you explain it by some idea, you are not going to reuse that information. Stuff like that. There's many features, many work we are doing just try to go along this way, to put it into one model.
Thank you for the great talk. Shapes make a lot of sense for problems like cars and letters, but you want to generalize this. So how would you talk about conceptualization, apply this to a totally different problem like recognizing spoken text, spoken words, rather than anything shape-based?
Yeah. First of all, we at Vicarious we haven't studied any speech, spoken language, or whatever things. This is not our focus yet. I think we will follow a similar principle. That is, we try to find the structure of the problem. More important, the structure of the data. That's like the structure of the data is a core number one structure of data of object is shape. There must be some structure, core critical structure for this for speech. We'll basically leverage Z and try to build a generative model out of Z, and that's the way we will handle the problem. And now we don't have it.
I'm just following up on his question about this kind of generative model would work well on shapes, which has like really distinct distribution, like A and B has very different statistical distribution. And I was thinking, like, would this advantage be able to translate into, say, a regressive model where you have a more continuous distribution rather than hierarchical distribution?
I think in a way that will be similar. Can I give a concrete example of this continuous? I think it's not going to be that straightforward because this is a case of just like last question. It's a case of we exploring the structure of the problem. But what you imagine could be a different structure of the problem. There must be a structure for speech. There must be structures for natural languages. And it's a core idea is that you have to efficiently explore the structure and encode that into your model and make it generative. Not always, but as a part of it, you make it generative.
Thank you. Thank you for the presentation. It was really, really good. I was just wondering, with Dr. Fei-Fei Li in your advisory board, if you guys have done any ImageNet, like comparison of the results. I mean, because she created the whole ImageNet data set, right?
Yeah, that's a very good question. No, we haven't. The reason is that, in our opinion, the ImageNet let's say in my opinion, ImageNet is a task you should solve at the end of the AGI road. This is the problem you have solved maybe in 20 years. You can try that.
A cool question. So, just looking at your generative model for image recognition, there's a similar project out of MIT called Picture. Are you familiar with it? And I was wondering if you can contrast. If you haven't heard of it, okay. So it's another generative model, but I was wondering if you were contrasting.
Yeah, I think there are a number of people doing generative model. We're definitely not a single one. I'll give you a few names. For example, Professor George Tenenbaum from MIT. He's a hierarchical generative model. He's a cognitive scientist. Yeah, I see. They definitely. We actually he actually visited us a few weeks back. There are a similarity of the ideas, the principles behind. Professor Zhu Songchun from UCLA also does something like this. Alan Yu, our advisor, also does something like this. So yeah, there are a few lines of work on this.
So you've used the letters as your sort of atomic component to analyze and build up to the word. Have you thought through the possibilities of building the object at the word level? Because it would seem to me that the way I read, at least, I think the way humans tend to observe or recognize objects, the written word especially, is at that object level. We're not seeing the A's and the B's, et cetera. We're seeing the word. So have you thought about the modeling of the word at the word level?
Yes, and so we have this kind of a way of a hybrid of a generative model and discriminative model, right? Our lower ladder model is generative, and our parsing model is discriminative. Ideally, what I would hope to see is that so the whole part can be made generative, because this is how we actually imagine seeds. If I ask you right now to imagine Vicarious, how would you do this? It's not popping into your eyes right away. You actually try to imagine VICR, it's like kind of a sequence. So in the ideal model of this syntax is going to be something I call it like a sequential vision model. It's just a sequence of reasoning. And you're actually creating letters one after another. And it is also based on the question you're asking. If you're asking that I want you to imagine Vicarious, then you will imagine such a sequence. But we are actually now working on such a sequence model for this kind of task. But at that time, there's no sequence. That's why we did this kind of a hybrid or intermediate way.
Thank you for your talk. I have two questions. First question is that would it be fair to say that your approach actually trades a large training set with manual feature extraction? And that's actually the missing thing in this whole thing. And actually, that's what explains why you need so little data in order to train your model. That's my first question. And the second question is that how does this approach connect to other approaches in other fields, like one-shot learning and few shots learning? Pilar.
Yes. Excuse me. And so first question is, I can answer the second question first. So the relation to one-shot learning, so one-shot learning is another a different story. It's basically about how you train on something, you're given something new, people recognize right away, or you can easily transfer your knowledge. Actually, we have that a part of it already in our hierarchy. When we have built a hierarchy, we can easily do one-shot learning. When we put these two together, we can easily do one-shot learning. So this one-shot is something we do as an extension to this work. The first question is whether we win because we do feature engineering. First, I would say no, we do not do feature engineering at all. Why? And we will never win by feature engineering. Why? Because before the deep learning or neural network took the best result in ICTA, there have been many people doing this kind of work already, doing feature engineering. And they are basically doing the classical vision approach of engineer features followed by a spot vector machine, always like this. But they cannot beat deep learning, which can do end-to-end prediction and more important, feature learning. What we do is actually not the core is essentially the shape part, the modeling part. That's how we win. Because our feature actually very simple. In the first, go far away. In that page, there's we only use 16 oriented filters, 16 angles. That's all we need. And what's important is the connection between them. That's the most important part. We don't use any fancy features. We don't use any corner detectors, whatever.
Okay, so I actually have two questions as well. So my first question is, specifically when working with this, I understand that you are still using kind of a more basic feature representation, but have you considered or experimented at all with the idea of using semantic or kind of lexical context in the actual generative stage to kind of add some more higher level, or I guess hierarchical information? And if so, how did that work? I understand that might be kind of out of scope of this exact example of this, but I am curious to see how it might augment it, considering that in the previous examples, when you do have occlusion, you are missing the centers of the word. And something like that may, with a greater context, be useful. The second question I have in this is, how does this compare to using a system where instead of manually selecting the features, you use something like a restricted Boltzmann machine or an autoencoder, and actually memorize the internal shape of, say, the thing you're trying to actually use, and then apply some sort of noise or actually perturb the weights inside of the network? Do you know if there's any existing work that does that, and if so, how does it compare?
First question, I think the answer is similar to the one answer to this gentleman's question. It is basically, if you want to add more semantic or like context information, we will do it. What I would do is basically add a sort of a sequential vision model. I think that would definitely help, like the scenario you described. Second question, I don't remember exactly anyone has done those kind of data set using autoencoder IBM. But in general, I find that autoencoder IBM is hard to beat. It's hard to beat CNN using them. In general, I mean, not always. In general, so if CNN we can beat the CNN, we can probably be better than them.
Thank you.
Thank you.
Hi. Your talk was really good. So what I wanted to ask was, what part of the shape model basically helped you get rid of the training data the most? Was it those red lines, or I guess my question is, like, do you have specific features in the shape models that are strongest in terms of weight, or?
Yes, I got it. No, we don't have any. We don't have weights in the whole model. We do not engineer features. We only just set one set of features. There's a 16-oriented feature filter. That's it. And your first intuition was very correct. And the critical part is exactly those lines, the way you constrain the shape.
Right. I guess my question was more like whether you have weights, but rather if you remove some of those, which are the, like, when does the model break down? And
see, if you remove too many of those lines, meaning constraints, the model can be extremely flexible. Then you may get a lot of false positives. Then the parsing may be too difficult because you're not looking at the right thing. If you add too many lines, the model is too constrained. It means you essentially cannot move at all. Then you also cannot deform with those kind of some variations or noise.
So how do you decide, like, what is the ideal?
It's actually empirically set. It's just about 2 parameters in our model. We just empirically tuned. It doesn't know. It's just 2 parameters.
So do you use like the small training data set to decide that?
I don't. We actually didn't validate that part. We just almost like 2 numbers we put there. It works pretty well for many areas. I think the core message here is that it's not a single line or single constraint that functions. It's them all together. So if we just put a certain range of values, it will also work fine.
Next question.
Hi, thanks for the talk.
Okay.
Quick question also, like, so how would this approach be applied to handwritten text? Right, my handwritten is very different than anyone else. And so that's one. Second, regarding, let's say, classification, I didn't really understand what you said regarding ImageNet. Let's say, how would you apply such approach to not 1,000 classes, but let's say 2 classes between 2 different types of dogs who look very similar?
Yes. First question is second question. If I think recognizing like a different type of dogs, they look similar, and they what's different is only at the very details. I think, there's a different way of answering. If you just want to solve that problem using discriminative learning, it works fine. And for our case, now I'll give you an example. If I ask you to imagine what a police car would look like, how would you do this? You will let me just assume you will probably first imagine the car shape and stuff, right? Then you will imagine you are adding details. You may add this siren, you may add this color, you may add this San Francisco police, those kind of details. That's how you imagine it. So to solve this problem is actually a sequential reasoning problem. You have a basic shape plus details. The details could be discriminative features, discriminative information. You will actually add it there. So this is also the way of you do this kind of task. So this is by the model itself right now, it's not sufficient to do that. Pardon, what's our first question again? Oh, handwriting and handwriting is handwriting recognition is always hard in practice, I would say. And our model can do it to a certain degree is okay, but if you have extremely deformation and sometimes if it's hard for human to recognize it, or we cannot recognize. And handwriting is more of a sequential. It's because you have this process. You'll be able to somehow model this process. That's why you have this kind of there's this paper by, I forgot, this is also deep learning way of they will perform very well on handwriting recognition. It's also a sequential model. So you need somehow sequential information.
All right, last question. Anybody?
Yeah, thank you. You add a constraint. You said that automatically, but that's manually specified for each character, right?
Manually, it's like we are given clean images of each letter, and
for
the
each
whole
letter
process is automated.
Yeah, but the constraint you specify for a specific letter, that's manually defined.
There's no manual. It's just we have a way. We have some kind of a condition to satisfy. For example, if at a certain distance, you only need one constraint.
That's
some, yeah, it's just we just added greedily, a greedy fashion.
Oh.
We actually didn't really want to specify this whole or prove this whole process, but it's just a word of fire because it's not a single. It's not a single constraint that matters. It's all the whole thing together matters.
Okay, so. And for each shape, like you produce one graphic model or
yes.
a site, just one big model. Are you reasoning on one node or there is some extra node added?
When you are reasoning doing reasoning or let's say inference, you actually reason a whole model. You cannot reason on one single one because you are passing message from you to its neighbors, to neighbors, to neighbors, back and forth. Yeah, loop. It's a loopy belief propagation.
So for example, like a Bayesian network, you get one node probability, right? That's your inference, right? So is that what you done on your model?
You basically get it's kind of you are essentially matching this model to the observed image. You try to see which of those, let's say, these observed features best match the feature in the model, and altogether they can get a high score.
Yeah, that score is a node in the graphic model, or
the score is on the node of graphic model. Yes, the score is yes. So essentially, you can just count, let's say, some sort of a confidence, just a percentage of matches. You can say that.
Okay.
All right, that will be the last question. Thank you so much. Give another applause to Dr. Lou.
Thank you very much.
Thank you all for all the great questions, and thank you for coming. See you next time.